Hi everyone, I am Aditya. Today I am going to talk about the differential encoding. In standard digital communication, we usually represent data with the absolute voltage levels. I is a 1, low is 0, but relying on the absolute states create a massive vulnerability if the signal gets inverted during the transmission. Digital encoding solves this by throwing away the absolute status entirely. Instead, it embeds the data purely in the transitions, the changes between the bits. The logic for this is incredibly simple. When we want to transmit a logic 1, we force the signal to toggle to the opposite state. When we want to transmit a logic 0, we hold the signal exactly where it is. Because of this rule, the receiver does not need to know if the signal started high or low. It only needs to watch for when the signal flips. From a hardware perspective, this is very easy to build. It just requires a XOR gate and one bit delay, like a D flip. At the transmitter, we XOR our current input bit with a bit we just transmitted. At the receiver, the process is reversed. The receiver just looks at the incoming signal, compares the current bit to the previous using a XOR, and instantly recovers the original message. So why we should use this? The biggest reason is a problem called phase ambiguity. In wireless systems, using the phase shift keying, the receiver oscillator can easily lock onto the radio with 180-degree out of phase. If that happens in a standard system, everyone becomes a zero and your data is completely destroyed. But with the differential encoding, the whole signal flips upside down. The difference between the bits exactly stays the same. The receiver decodes it flawlessly even if the signal is inverted. Of course, every engineering design had a trade-off. The drawback here is error propagation. Because the receiver uses the previous bit to decode the current bit, the noise spikes corrupts it just one bit during the transmission. The receiver output will two consecutive errors. However, getting 2-bit error, which we can easily fix with the error correction rules, is a much better alternative than losing the entire signal to the phase inversion. To see how it practically works, let's look at the 8-bit byte. Our original message is 11010010. Before any transmission happens, the transmitter and the receiver must share a starting reference point. We will use 0 as our initial reference point. As a reminder, the XOR gate is simple. The two bits we compare are different, the result is 1. If they are exactly the same, the result is 0. Here is the step-by-step mathematics happening inside the transmitter hardware. For the first bit, we take our input 1 and XOR it with the reference 0. They are different, so we transmit a 1. For the second bit, our input is 1 and we XOR it with 1. We just transmit it. They are the same, so we transmit a 0. As we cascade down the entire 8-bit sequence, each new encoded bit depends on the right hand before it. Notice that our final transmission sequence is 1001100. Looks completely different from our original signal. Now the signal receives at the receiver. The receiver applies the exact same XOR logic, but it compares the bit it is currently receiving with the bit it received a fraction of a second ago. For the first bit, it compares the received one against the reference bit. There are different decoding a 1. For bit 2, it compares the received 0 against the previous. They are decoding another 1. By simply comparing the adjacent bits, the receiver perfectly reconstructs our original 8-bit message signal. As you can see, it recovers the original signal. To really prove by engineering, use this. Let's look at the worst case scenario. Imagine the transmission channel flips our entire signal upside down. Every one becomes a zero and the reference bit flips to. If we fed this completely corrupted signal in our decoder, the XOR math still works. Because the current bit and the previous bit we were both flipped, their relationship to each other remains identical. The receiver decodes the exact same sequence, saving the system for the catastrophic failure. As you can see, it is the requirements. Thank
Hello everyone. Today I am explaining the code. The main starting code is clear the all windows, and then we are figuring create a main figure window. The figure window is a create a statistics test level at the top left of the window, instructing the use of two type, and then H input. Explanation is create a editable text box. User type their binary number. It handles to save and H input. So script can be read what is the user typed letter if containing a default binary sequence, and the unique control. Unique control is a create a push button label. Stimulate the critical part is callback, which tells the program to run the simulation function where the button is clicked. Then AX1, AX2, and AX3. The AX1 is top plot, the original signal, and AX2 is the middle plot, encoded signal, and AX3 is the bottom plot, decoded signal. Then manually pulse the simulation function once right click the app opens, ensuring the graph aren't black to start up. Then function run simulation defines the inner function that process the data and draw the plots. The syntax ignores the automatically passed arguments. The object which triggers the callback is event data which aren't needed there. And get H input string. Grab whatever the text currently inside edit box as a string. Example ones and zeros. The strings to is a convert the text string uh, mathematically array of a number. Then it simplify input sequence. Any input sequence is equal to 0 and input sequence equal to 1 is a safety check input validation. If the user type letter the leave in a blank to enters number of other than zeros and ones, the error dialog box pop-ups and returns else executes before the code crashes. And end length input sequence measure how many bits are in the user sequence and store what count in n. Encoded sequence equal to 0, n is a pre-allocated and empty array of zeros. For an encoded sequence is also set up the ref bit equal to 0, which represents the baseline previous bit needed to start differential encoding. For I equal to n, for I equal to n, encoded sequence I is the XOR input sequence I reference bit. The loop through every bit is of the input sequence is applies the executive or XOR operation between the current input bit and the last encoded bit. The newly calculated bit becomes the reference bit if the next round. And the decoding stage. The decoding stage is the pre-allocated space for the output sequence and establishes the matching baseline reference bit. The reverse process box XOR ring is the current received encoded bit. The previous received encoded bit is successfully extracted and recovers the original data. And T is on O, N is a timer vector of a stair plot. Generate a time step to array from 0 to n to map out the duration steps on the x-axis and axis of AX1. Target to top axis AX1. It uses to stair generate a digital sequence square waves because the stair plot requires on extra data plot to an end to close the last step, and AX axis set the x-axis boundary for a 0 to n and y-axis from minus 0.2 to 1.2, and applies labels, bounds, and title terms into a guidelines and forces x-axis strict to step exactly integer by integer, and axis explains switch the focus on the middle axis AX2 to plot the encoded sequence using a red line with identical grid spacing the scanning constant, and end of the program is first and closes the run simulation, nested function, and final and use overwriting differential encoding guide program.
Hello everyone, I'm done with here. I'm going to explain the graph of this experiment and in the first graph and that blue line shows that original binary sequence. This is the raw data of the this is the raw data you want to send converted into a standard unipolar non-return to zero waveform when a binary is represented by high volume and binary zero is a low voltage and 0 to 1 is high and 1 to 2 is low and 2 to 4 is high, etc. And the middle graph shows that the differentially encoded sequences. This is the heart of the simulation, and the differential encoding doesn't care about the absolute level. It looks at transitions based on the specific graph's behavior. It uses the standard convention where an input of 0 causes a transition. And the uh, last graph shows that the binary sequences, and this is the final output after the receiver processes the incoming red signal. The receiver hardware looks at the red signal and compares at the current level bit to the previous bit level. And some of the applications of the differential encoding simulation are used in digital communication system and helps to reduce the transmission errors and used in PSK phase shift and applied in a wireless communication and networking improves the synchronization between the transmitter and the receiver. Advantages: simple to implement, better noise immunity, and avoids the polarity problem. In conclusion, differential encoding simulation helps to understand how data can be transmitted more reliably by encoding changes bits instead of sending the original bits directly. Thank you.